In this video, we are going to discuss about design of slabs. Slab is also a flexion member where the beam of width of the slab is designed. Slab is also designed as a beam, but our beam is normally 200 300 mm weight, but slab is having huge weight. So we will consider per meter width of a slab as a beam. Then we design the reinforcement, but reinforcement here the slab we will not calculate in numbers, but we will calculate in terms of spacing. For example, in beam we will say that 4 numbers of 20 mm diameter is required. But here we will say 16 mm diameter at the 100 mm center to center spacing. So which means at every 100 mm you have to place 16 mm diameter. This is how the slab design is done. In slabs there are two kinds, right? One way and two way. So for the time being we will talk about one way slab. So as I said, slab is designed as a beam of 1 meter width. So what is this one-way slab is all about? We will talk about one-way slab, then we will talk about two-way slab. So one-way slab is a slab. Any slab consists of two dimensions, right? So I am talking about plan. Now we have to talk about beam cross sections and longitudinal sections. Now in slab we will talk about plan. Plan is nothing but when we are viewing the structure from top, right? So normally we have two dimensions to it. So and that dimensions are divided into short span and other as long span. Normally long span is designated as Ly and short span is designated as Lx. We have to remember this. So what is Ly? Ly is long span. What is Lx? Lx is short span. Now how you can tell one of the dimension is long span and short span? So the highest of the values of the slab dimensions could be the long, and the lowest value of the dimensions of the slab will be the short span. For example, if I take this value as 3 meters and 7 meters as the dimensions of the hall, then long span being 7 meters and short span being 3 meters. So what is the condition of determine whether it is a one-way slab or a two-way slab? So condition is if Ly by Lx is greater than or equals to 2, then that slab is termed as one-way slab. If longer span by shorter span ratio is greater than or equals to 2, then that slab is termed as one-way slab. If, in the same condition, if longer span by shorter span ratio is less than or equal to 2, then that is termed as two-way. Then what is this one-way and what is this two-way is all about? Now imagine you are holding a piece of plate. Now that is the slab. Now if you load that plate, now it bends like a saucer, right? You have a tea and a saucer, right? Cup of tea and saucer. Now how the saucer bends, right? It's in a circular shape. In the same way, your slab will also bend. So in two-way slab, the slab will bend in both directions, that is longer span and shorter span. Whereas this one-way slab will bend in only one dimension, that is along the shorter span. So the so-called the reinforcement is also provided, which means in two-way slab the reinforcement, which means main reinforcement, is provided in both directions. Whereas in one-way slab you need to provide main reinforcement in only one direction. The other direction you can provide it as a distribution steel in order to hold the main steel bars and also to stop the slab to control the slab in shrinkage and temperature effects. Fine. So I have got here 3 by 7 of dimension slab. Right? So if you divide it by 3 by 7, the value is more than 2. So that slab is a one-way slab. So as I said, for one-way slab, the reinforcement is provided in only one direction. So in one-way slab, the reinforcement is provided in only one direction, and that is called as a main reinforcement, and it is also called as transverse reinforcement. And in other direction, the reinforcement provided is called as distribution reinforcement. Sorry, this is not transverse reinforcement, this is longitudinal reinforcement. This is called as transverse reinforcement. So, as I said, if you consider this slab will bend in 7 meters direction. So the main reinforcement is provided in opposite to it, that is in shorter direction we will provide the steel. So alternatively bars are bent and the main steel is provided in this way. So this is provided in entire span from here to here. This is distributed. This is main steel. Right? Whereas distribution steel is provided in right angles to main steel. That is, this is distribution steel. When you compare a one-way slab with a two-way slab, there will not be no distribution reinforcement in other direction. In both direction, that is in longer span and in shorter span, main steel is provided. When in one-way slab, main steel is provided along the span which is shorter. In longer direction, distribution steel is given. Let us do one problem for our understanding. Now, before doing one problem, I will list out the steps which are involved in design of one-way slab, and we follow the same procedure in the subsequent problem. So, please copy down the design steps. So first step is to enumerate the design constants. So what are the design constants? Design constants are F, C, K, F, Y, and what what else we have? We have x max values. These are all values we need to calculate, right? Now, if it is not given, we have to assume it and we have to start doing it. Next, you need to calculate the design bending moment and shear force. Design bending moment is we need to multiply with the partial safety factors and you have to calculate the design bending moment and shear force. Now, the third step is you need to calculate the effective depth. Now, effective depth is assumed based upon serviceability criteria. L by D ratios are given in your code book. As per the IS 456 L by D ratio, L by D is span by depth. Span by depth is given for simply supported beam as 20 and for the continuous beam as 35 something. We have to refer the IS 456. With reference to that, we can easily calculate the effective depth. Now, the fourth step is B. When you know the effective depth and when you know the design bending moment, you need to check whether the provided depth is good enough to take the required depth. So, in effective depth calculation, we will calculate the required depth, right? And for the given bending moment, we will sort out in the game. We will know when we are doing the problem. Okay. When you got the bending moment values, you can easily calculate the reinforcement. So reinforcement design will again consist of main reinforcement and distribution reinforcement. And when you have completed this, 90% of job is completed. Now you have checks for deflection, you have check for shear. This will be discussed in the later parts. Okay. So at the time being, we will discuss one problem. So please copy it down, dictate it. Please note down this problem. Design a RCC slab. Design a RCC slab for a given data. Design the RC slab for a given data. Room dimensions, below you write down room dimensions 3 by 7. 3 meters by 7 meters. 3 by 7. Wall thickness, you have the slab is provided on this wall. Wall thickness is 300 mm. Wall thickness 300 mm. Lime concrete finish, which means slab over slab, they have finished with lime concrete. Lime concrete finish 75 mm thickness. Over slab 75 mm thickness is there. You have to consider that also in the design part. Unit weight of lime concrete. Unit weight of lime concrete. Whatever the finish you have done, that unit weight is 20 kilonewton per cubic meter. 20 kilonewton per cubic meter. Live load on slab. Live load on slab 2 kilonewton per square meter. 2 kilonewton per square meter. Take M20 grade concrete and Fe415 steel. Take M20 grade concrete and Fe415 steel. So the same dimensions we have taken, and so what kind of slab we have got now? We have got a 1-day slab because Ly by Lx, if you calculate, it is more than 2.2. So first we will write down that. So longer span by shorter span ratio, that is longer span is 3, 7, shorter span is 3. You can directly write this value is greater than 2. So this slab is one way. It bends in only one direction. Reinforcement is also provided in one direction. Right? Now, what are the design constants? Please write down. What are the design constants? You have given the FCK. FCK as how much? It is 20. Now, Fy as 415. Now, what is this XU max? XU max depends upon the grade of steel. Now, for Fe415, for IS code, you can take as XU max by D equals to 0.48. This is again the design constant, right? Now, third is what you need to do is you need to calculate the design bending moment and shape force. In order to do that, you need to do the loading calculation. How much load actually slab is carrying, right? And before calculating the load, you need to calculate the dead load. Without knowing that, you cannot calculate dead load. So, from serviceability criteria, L by D is 20 as because this slab is given as simply supported. If it is not given, you assume it as a simply supported. If L by D is 20, then L is given as 3 meters and the wall thickness is given as how much? 300. So which means this slab is resting on a slab, right? And this wall is 300 mm thick. So from here to here would be 3 plus 0.3 plus 0.3, that is 3.6. That is overall. From center to center would be 3.3. Okay, so 3 plus 0.3 by 2 plus 0.3 by 2. So when you are taking L value, either you can take 3 meters or either you can take center to center. So preferably I will take center to center distance. So center to center distance is given by 2300 divided by 20 will give you the depth. So if you calculate this, D is coming as 165 mm. So from serviceability criteria, it is recommended to go for a slab thickness of 165 mm. If you know this D, then you can calculate overall depth as how much? D plus D dash. So D is given by 165. D dash is given as normally for beams 25 mm clear cover is taken. For slab clear cover is normally 15 mm only. Plus you have to take the diameter by 2 because there is no shear reinforcement here. So you will take half of diameter, that is normally for slabs 8 mm or 10 mm is taken. I am taking 8 mm. 8 by 2. So overall depth you will get as 165 mm, 176 mm. So let us take overall depth of 176 mm. So you can calculate here effective span. Effective span is taken as least of the following. One is center to center span. Second is clear span plus effective depth. Now center to center span is 3 meters plus we have just discussed before how we got this 3300 plus 0.3 divided by 2 will give you a value of 3.3 meters and clear span is given by, this is clear span and effective depth is 0.176, so So this is 3.176. So least of these values is taken, not highest. So the effective span is 3.176 meters. Now where it is useful is when you are calculating the bending moment, WL square by 8, this you have to take. So effective square is normally denoted by LEF. Now we need to calculate the load calculations. Right. So first we will calculate the dead load of slab. So overall thickness is 176 mm. So 0.176. We will take 1 meter breadth, 1 meter width, and this should be multiplied by density of steel concrete, that is 25 kilonewton per cubic meter. This will come around 3.125 kilonewton per meter width, because it is 1 meter width. After dead load of slab, you have live load on slab. Live load on slab. Live load on slab, in the question it is given as 2. So 2 multiplied by 1, simple. So it will convert to kilonewton per meter. Then we have got the lime concrete finish. Lime concrete finish, that is thickness of 0.075 mm by 1 into density is given as 20 multiplied by 0.075 will give you a value of 1.500 kilonewton per meter. Now if you add these three, then you will get a value of 6.625 kilonewton per meter, which is a working load. Now ultimate load is given by (1.5) multiplied by working load, that is 6.625. If you multiply 1.5 with 6.625, you get 9.94 kilonewton per meter. Now if you know the ultimate load value, then you can easily calculate the ultimate bending moment, ultimate shear force. So ultimate bending moment is given by W, that is, this is W, L effective WL square by 8. Similarly, ultimate shear is given by ultimate load L effective by 2. So substituting 9.94 into 3.176 square by 8, you will get bending moment value 9.94 into 3.176 by 2, you will get ultimate shear value. So ultimate bending moment value is given as 12.53 kilonewton meter, and shear force is 15.78 kilonewton. So you have got ultimate bending moment, ultimate shear. Now design of, so you need to calculate whether this D provided is good or not to take the 12.53 kilonewton meter, because this you have assumed from serviceability criteria, you have not designed it. So now you have to design the depth for 12.53 and whether it is suitable or not, we have to check it. So we will check from assuming this section as a balanced section. So assuming this section as balanced section, right? 0.36 FCK X max by D into 1 minus 0.42 X max by D multiplied by B square. Now we will equate this balanced movement to the ultimate moment, that is mu 12.53 into 10 power 6. 10 power 6 why? Because mu kilonewton meter is converted to Newton mm. All these values are Newton mm. Equals to 0.36. FCK value is how much? 20 into X max by D is 0.48. 1 minus 0.42 into X max by D is 0.48. Breadth in slab, breadth is 1000, right? For 1 meter we will design 1000 into D square. Now from here to here, if we solve that, the required depth, this is provided depth, this is provided. Required depth, you can get it as 67.37, right, mm, whereas this is provided is much more better because on safety side it is good. So it is required only 67, but we have provided 165, so it is safe, right? You write down here, hence safe. Now you have checked the depth. Now you need to calculate the, you have calculated the effective depth here. Now you have, then you need to design the reinforcement. So reinforcement design. So in the reinforcement design, you need to design for only main steel. For main steel, right, you need to consider this moment, and for that moment you need to calculate. So it is up to you whether, normally slabs are designed as an under reinforced section because it gives 3 default if it is a balanced. Steel can be a little bit less, but if you take under reinforced section, you will provide more steel. So it could be on a safer side, right? Steel phase first is first priority, not the concrete. So assuming or designing the section as under reinforced section, designing the section as under reinforced section. So movement of resistance for under reinforced section is given by 0.87 FYAST into D minus 0.42 XU. Now this equation is different when we go to code, but the value will be the change. So you need to express the values XU in terms of AST, then you have to back substitute here. Now XU we know as 0.87 FYAST divided by 0.36 FCKBD. So D is not as here because in code book it is given something like here. So D will get cancelled. Now 0.FY is 415. You have to keep AST same. Divided by 0.36 into FCK20. B is how much? I said 1000. Now this value will come around 0.0502 AST. Now back substitute XU here. Now replace MR with MU. So MR equals to MU equals to 12.53 into 10 power 6 equals to 0.87 into 415 into AST. You need to calculate AST. D is how much? 165. Why I am taking it is in all values minus 0.42 into 0.0502 AST. Now this will give you a quadratic equation. Now quadratic equation has two roots. In them the least value is taken normally. So AST you will get very less as 34 mm square. Now this is required. This is required. Now this AST should be required in this much, but minimum value you have to check, right? So the minimum value is given as, so minimum AST depends upon the grade of steel you have used, right? So here in distribution steel, please make a note of this in here. Distribution steel, if you are using mild steel, you have to provide 0.15% of gross area. If you are using HYSD, you have to provide 0.12%. So this is for Fe250 and this is for Fe415 and Fe500. And what is this? This is against gross area. Right. So minimum for Fe415 it is HYSD. So it is 0.12%, 0.12 divided by 100 into gross area BD. BD. So 0.12 divided by 100 into 1000 into overall depth is 176. You will get as 211.2 mm square. So this is the minimum area which is required, right? So we will provide this area because this is very too small. So when you provide this area, you can calculate spacing immediately. So when you wanted to calculate spacing, so you have to assume diameter, assuming. Now we have assumed here as 8 mm. So we will take say that assuming diameter equals to 8 mm. So how do we calculate this diameter is, you have to, in numerator you have to put the provided diameter, and below you have to put the required diameter. This much amount you need to have, this is the diameter you have assumed, and you have to multiply it by 1000. Then you will get the spacing. You have got 237.99. So I am taking this as 225 mm. So always keep these values in multiples of 25. So how did I got the spacing? Spacing is given by whatever the diameter you have assumed, keep that cross section area in the numerator, and whatever the area you have designed here, either this or either, if this value is more than this, then you will consider this value. As because this value is less than this, you have taken the minimum value, and provided divided by actual required into 1000 into, you will get the spacing. So write down a statement here. Provide 8 mm diameter at the rate 225 mm center to center as main reinforcement. Now you need to supposed to calculate the distribution steel also. Now as I said, distribution steel you have to take this much percentage, right? Now for given grade of steel, that is Fe415, distribution steel is also 0.12%. So the same we will repeat again this step. Distribution steel area is also 11.2. The spacing will also be same. So you can provide 8 mm at the rate 25 mm, 225 mm center to center as main reinforcement and distribution reinforcement. So we will do one more problem.